So next up we have Mike Bell from ICIT up in Orkney, Harriet Watt. Mike will be talking about the management of sustainable fisheries alongside marine renewables and modelling spatial interactions.
Good morning, everybody. I'd like to start by acknowledging my two co-authors here, which is Professor John Side, who's my colleague at ICIT, which is the Orkney campus of Harriet Watt University. We're also working with Kate Walker, who's employed by Orkney Sustainable Fisheries, who's working very closely with us on inshore fishery management in Orkney. I don't think I need to waste too much time setting the context here. I think it suffices to say that we have a traditional and a new emerging user of sea space here, and it's extremely interesting to consider how these two sectors might sit alongside one another. I think it's also not too controversial to suggest that the greatest potential for interaction between these two sectors is likely to be in inshore areas. And it's relevant to point out that here in a Scottish context, we have these new inshore fishery groups, and comparing these two Marine Scotland maps, I think it's fairly clear to see that their areas of interest are somewhat coinciding. So really it's the spatial overlap that is our first consideration here. And there are good data emerging on this. We've already seen from Ian Davies the ScotMap initiative from Marine Scotland. In Orkney we also have the Orkney Fishery Project, which is funded largely by the Crown Estate, and also supported very well by others, including Marine Scotland, providing VMS units for vessels. But given that we have spatial overlap, what might be the challenges and the opportunities for fishery management? Well, I'm going to show you some results of a very simple spatial model, which provides some fairly obvious insights into this. So when I say it's a simple model, I really do mean it is a very simple model. Here we have essentially four states relating to, essentially we have four states here relating to what a fish or a shellfish is doing at any given time. It can be alive in an area that's either open to the fishery or closed to the fishery, or it could die, either because it's caught by the fishery or because it's dead for other reasons. And alongside that we can model other biological processes. So what's that got to do with marine renewables? Well, we might consider that marine renewables are likely to displace some fishing activity from their traditional grounds, and we consider that as a kind of closed area, whether it's defined as such or not. So we have this very simple model. It's also worth noting that it's a spatial model, and there's more than one kind of space that we're dealing with here. We've got the traditional space, geographical space, and that's really the arena for human activities. So in our model terms, that's where we define the closed areas, the renewable energy developments. That's where we define fishing as happening. But we've also got this rather more elastic kind of ecological space, which is the arena within which the target organisms have their activities. And we can define that in terms of the relative carrying capacities of the environment inside areas that are close to the fishery and inside areas that are open to the fishery. And these two kinds of areas are very relevant. The first, being the arena for fishing activities, that if we change that, that's a modifier for the harvest rate, which is the pressure on the stock. And the second is what really defines the nature of exchange of animals between the open and the closed areas. It also allows us to consider changes in the quality of the environment in the different types of area, which I might loosely define in terms of reef effects. And before going on to look at the outcomes of some of these models, just introduce some concepts related to sustainable fishery management, well, we have the MSY, maximum sustainable yield approach to fishery management, which is used worldwide. It's the basic principle under which fisheries are managed in the United States. It's the basic principle under which EU fisheries will be, to some extent, are managed. And it's also the basis for things like the Marine Stewardship Council criteria for accreditation of sustainable fisheries. And underlying that, at the core of that, we usually have a harvest control rule, which controls fishing effort. And that generally relates to two kinds of criteria, a limit and a target. And the target generally relates to fishing mortality, and it's fishing mortality that we expect to deliver maximum sustainable yield. In practice, we don't often have enough information to be able to define those targets or limits very clearly, but very often have good proxies. And good proxies, particularly for these target reference points. And that's something we can very easily look at in our spatial modelling context. So I'll be showing you some candidate proxy values for these target reference points that emerge out of these spatial models. So just a little bit more on that. So these are the kinds of proxies that we have. Effectively, they're curves of relative spawning potential and relative yield. And each of these is a per recruit analysis, which essentially means this is the amount of spawning biomass contributed for each fish that recruits to the fishery. And this is the amount of yield to the fishery that is contributed by each recruit to the fishery. And in the absence of knowledge about stock recruitment relationships, that's a good proxy for spawning potential and relative yield. And we can define reference points on these curves, which excuse me, are good candidates as target reference points. So here we have the point at which relative yield is maximized, and a slightly more conservative reference point here relating to a particular proportion of the unexploited level of spawning potential. So we can define points on these curves. And this example is calculated using biological parameters for Orkney lobster stocks, which is quite a good candidate for having relevance to interactions with marine renewables. So let's start introducing some spatial terms into that. What happens if we close off quite a large area, 20% of the grounds to the fishery? Well, in order to be able to say something about that, we need to say something about how much exchange there is between the open and the closed areas. So here we define something that's relatively sedentary. We're saying there's a small leakage from a closed area on a daily basis, only 1%. And you can see closing that area has virtually no effect, either on the reference points or on the curves themselves. And that's even at this very low rate of movement. And that's probably being very optimistic about how faithful these lobsters might be to an individual area. So any higher movement than that, you're certainly not going to see any effect at all. Well, so far, so not very interesting, though I guess it could be somewhat reassuring. So let's move on to start introducing some biology into here. What happens if we consider that the area that's close to the fishery might actually have some increased habitat value, a kind of reef effect? Well, in this case, if we say that the habitat has double the value per unit area, we get some change in these curves. We get rather more resilient, we get rather more resilience at the higher levels of fishing effort. So this green curve rises above the baseline for both yield and spawning potential. And this changes the locations of our target reference points. So we would likely to have management which allows higher levels of fishing pressure. So essentially it's greater resilience for the fishery. And that might be thought of as quite a realistic scenario. But it's not the only way in which we might introduce a bit more biological realism. Well, all lobsters aren't equal. There's been quite a lot of experimental evidence which shows that some lobsters are pretty sedentary and some lobsters move about quite a great deal more. Well, if we start introducing that kind of movement heterogeneity into our models, what happens? Well, again, we get some shifts. Keep on pressing the wrong button there. Shifts in our curves, which increases this spawning reference point quite well. Doesn't have a big effect on the yield reference point, but it is at the expense of some loss of potential yield. So we do have some enhanced protection if we introduce that little bit of biological realism. Well, let's introduce further layers on this. Let's suppose that inside the closed area, we've enhanced the value of the habitat, perhaps through structure introduced from renewable energy development, perhaps deliberately. So perhaps the lobsters in there are going to move around a little bit less. Well, here we get quite a dramatic effect for this particular scenario. We hugely increase the value of the spawning reference point, and we can see where the spawning stock becomes hugely more resilient to fishing. It is at the expense of some loss of yield, though, relative yield. It is worth noting, however, that is relative yield. And if we are actually increasing the value of habitat inside this closed area, actually we might, even if we don't know much about the stock recruitment relationship, we might be releasing some habitat bottlenecks for recruitment. So in lobsters, for example, shelter for juveniles is likely to be an extremely important bottleneck for the population. We're likely to increase recruitment if we start introducing new habitat for juvenile lobsters. So we might actually expect some of these losses in relative yield to actually be compensated, not to be realised in terms of absolute yield. So what have we learned so far from that? I need to say straight away, what we've learned so far is highly dependent on an important assumption about the fishery, and that is that fishing effort displaced from a marine renewable energy development or from any closed area can be freely distributed across the fishery. Now that is quite important in that if it isn't the case, then actually we are reducing the value of the fishery, while reducing the amount of fishing effort. And it's by no means certain that that assumption is justified. Fishing effort is not so transferable between areas as might be generally supposed. But given that assumption, we have a few conclusions here. Firstly, that if there's any appreciable mobility between open and closed areas, the closure is probably going to have very little effect on our long-term yield or spawning potential, or for our management criteria. But significant differences in mobility effectively creates a pool of stock inside the closed area which is less accessible to the fishery. That's going to increase resilience, at least at a moderate fishing level of fishing effort. And it's going to allow us to relax some of the reference points for the fishery. And if we actually are enhancing habitat quality within the closed area, for example, through increased structural complexity around a development, that can increase the effective size of that closed area in terms of its carrying capacity for the stock. And there we have, in particular, big gains in spawning potential at the expense of some possible reduced yield. But again, I'll reiterate this possible reef effect, which can release population bottlenecks, so absolute yield may in fact be at least compensate for that, or possibly even increase. So a few final thoughts. I don't think anything too controversial here, but inshore fishery managers, and in the Scottish context, it looks like we're actually going to have inshore fishery managers emerging. They actually need to understand the implications for these spatial interactions with a new industry and their environment. in order to be able to put this in quantitative terms, we actually need a great deal more understanding of particularly how fish and shellfish move across the ground. And there is research going on. For example, this CubeX consortium, which is funded by the Natural Environment Research Council and DEFRA here in the UK. It's led by David Sims at the Marine Biological Association. That's actually doing quite a lot of work tagging fish and shellfish and looking at their movement patterns in relation to renewable energy development areas. Then finally, again to reiterate this importance of the potential importance of habitat enhancement. And this is a real opportunity, I think, for positive interaction between the marine renewable energy sector and fisheries. And there is some research going into this. In Orkney we have a small research project which will be starting shortly, where there will be artificial habitat placed on the ground, and we'll be looking at the potential benefits for juvenile lobsters. And now we're finished. Thank you.
Okay, thanks, Mike. It's quite interesting, quite a few parallels with the discussions that we had yesterday at the Annex 4 workshop in terms of the moving line interactions there, so interesting to see the perspective there.